Welcome to our instrumentation lab. Here's your unknown. Go figure out what it is. That's exactly what we do here, right? That's the reason we enter an instrumentation lab. So there you go. So that's, usually when we walk into the instrumentation room from the organic lab, it's because we've painstakingly tried to purify something and we want to confirm its purity, or we've tried to synthesize something and we want to confirm its formation, or we've isolated or extracted some oil or something from a natural resource and we want to know what is even in it. What is there? We have no idea. So we're not even confirming, we're trying to identify what it is. So those are the three main reasons we enter the instrumentation room, right? And so we are going to do some unknowns, a lot of them, so in the form of getting the resulting spectra that come out of the instrumentation room. Okay, so this is our lovely GCMS, and it's a great instrument, and it's one of our favorites, very powerful. The GC part, we're not focusing on too much today, but it means that it has gas chromatography coupled with the mass spectrometer part. So that means it can actually separate. So if you put something in there that's not pure, then it can separate it as it goes along before it hits the detector to identify what the mass spec is. So that part is going to be another discussion, but mass spectrometry is the focus for today. Okay, and listen to that word. I'm going to say goodbye to our lab. Mass spectrometry. Oh, and by the way, this is the cute one they have in the virtual client. It looks a lot smaller because it's just mass spec, MS, no GCMS. So that's what I wanted to bring that up because we'll see both of those kind of pop up now and then. Okay, so listen to that word. Mass spectrometry. How does that sound different than the instrumentation techniques we have learned about so far? We've learned about IR spectroscopy, NMR spectroscopy, UV-Vis spectroscopy. Now we're going to talk about mass spectrometry. Different ending, different suffix, right? There's a reason for that. It's not tonoscopy. That means we're not using light to understand what is going on. We're not using light energy. So just as a quick recap, if we were to go into the lab, I'll just do it off on the little margin here, and I give you a, let's draw that or little Erlenmeyer gave you a test tube this time. Here's our unknown. You could go in there and you could do, I'm going to take an NMR, right? So let's make the NMR blue. Incoming radio waves is part of taking an NMR. And then the molecule responds to those incoming radio waves. It actually absorbs some of the energy, and what does it do to release it? When it absorbs it, it flips the spin of the nuclei. And you watch how that response is different from molecule to molecule and how that can differentiate different atoms. That is interesting information that gives us information about the structure. It's a resonant frequency thing, right? What if we did IR? I'll make that red since it has red in the name. I'm drawing a smaller wavelength on purpose. IR, as the name says, is infrared radiation, right? Once again, part of the light spectrum. And the other one we've also learned a lot about is UV-Vis. And that's the higher energy one, so it's smaller wavelength. And that's also useful because they all do different things, but they're related in that you put in light energy and the energy in, some gets absorbed, and so the energy out will be different. And the detector, I mean, it's a lot more complicated to work out how that all works out, but that's the overall big picture, right? And the detector picks up what was actually absorbed and why that's interesting. That's what we're supposed to interpret. So we get the consequence of that. So think about that for each case. NMR, it flips the spin. IR, you see those molecular vibrations. UV-Vis, conjugated molecules, that's when it's most relevant because it's in that energy range where you will see the per motion of electron from the HOMO to the LUMO. So that's the ground state to excited state, and then the spectroscopic analysis could include what was absorbed or how the energy was released, and so on. That's all interesting information. When nothing happens, we don't have a resonant frequency, and that's not interesting. So that's why these particular frequencies are needed to probe it. Mass spec is not going to use anything from the light spectrum. So there's also X-ray crystallography, by the way. So which I haven't talked about yet, but that's another one that's in the light spectrum. But mass spec actually uses very high energy still. So that's why it's in the same ballpark as like a spectroscopic technique, but it doesn't use light. So it uses a high energy, actually I think it's around 70 electron volts to actually blast apart the molecule. It's almost like a reverse engineering. So if you don't know how something is put together, it's sometimes useful to take it apart. And that's what it does for us. We don't know what the total molecule looks like when we use the mass spec, but we get to find out what the pieces look like. And then we can come up with a logical way to put it together based on how it would have been best to break it apart. That's called fragmentation. So those are 2 reasons we would do this. Okay, so we do this to look at the pieces and also to get mass information. And the mass can help us understand what's going on with the formula. So that's the recap leading into this. That's our backstory. And before I go straight, these go straight into examples, and that's really the best way to practice this. I'm going to do a little bit more background, and we'll come back to that, okay? So let's get to here. So I was trying to describe that, and the visual is a little easier. So you get your sample in there, and you get this high energy incoming electron volts. You can actually knock an electron out. So a lone pair is kind of drawn in here, but it could be a bonding pair. But 1 electron is ejected. All right, so it's gone. So now you have, you can't keep the bond with only 1 electron, so it fragments. But you briefly have what you can identify as the molecular ion. And it's a radical cation. It's a radical because it's missing that electron. And so the cation is because 1 piece will have to be charged as it separates from its other piece. And the cations are something that can be detected by the detector. So it picks up on the charged pieces. It does not look at the radical pieces, but you can actually guess what it was by the one that didn't show up. So we'll go through some examples of that. Okay, so you are able to pick up on what cations were formed. So that's really what we're looking at. When you see a peak, that's a cation that formed when it broke apart. So it's not the original molecule, it's the cation that formed when it broke apart. The closest thing we'll ever see to the original molecule is if we get to see the molecular ion peak, which doesn't always happen, and that's because one electron got knocked out. And that is essentially the same structure, structural information as the whole molecule. So that's very useful. Okay, so let's expand that cartoon to see what that means at the molecular level. At the molecular level, okay, there's my 70 electron volts. I thought I remembered that, right? That's enough to bump an electron out. And so what does that do? There's a little schematic. So this is represented in brackets because right now we're not assigning the charge because this is the molecular ion. And the molecular ion we call M+. So also known as the parent ion. So I'm going to write that down. Oops, get that up here for you. Molecular ion is also known as the parent ion. And it's abbreviated the M+ peak because it's the M was the peak before it got, so we could call this M. It would have that mass, but then we would say this is the M+. So we lost the electron. Okay, so here's that electron we lost. Because we lost 1 electron, the M has an unpaired electron. So that's the resulting unpaired electron. Why is it a cation? It helps to look at what happens when you knock an electron out of a bond. So I'm going to expand this a little bit more so we can kind of imagine the mechanism. So I'm going to redraw this right here in the margin. Oops. And This is a generic alkyl, like branched alkyl molecule. Now, if we have to break one of those bonds, and I've really only given you a choice of one because we don't know what those R groups are, we're going to break this one because it's tertiary now. It'd be a tertiary carbocation if we had to. We don't know what this was, which is why, to keep it simple for our first look at it, we're going to break only the one that we see here that's fully filled out. So it would be tertiary. And now let's show how that works. Well, I'm going to take you back to Chem 60, or your introductory chem, for just a minute, because this line, don't forget, that means carbon with a bonding pair. That line means a bond of using 2 electrons. Right? Remember that? And it was really cumbersome to always write it that way, so we'd replace it with a line. But that's really what that means. And the reason it's useful to write that now is because we actually are ejecting only 1. You don't have a bond anymore when you take that 1 out. Here it is. So they are already effectively separating, and one of these 2 guys is going to get the radical. The other one's going to get the cation. And so in reality, they might take turns. It might break asymmetrically, or you might actually break it symmetrically. You might actually see sometimes one gets the radical, sometimes one gets the cation, and in that case, you see a peak for both of them, because remember, we only see cation peaks. So what is a way that this would look when it finally fragments? So this is when it's kind of still together, but just, it's not something you can isolate by any means. But when it finally fragments, I'm going to fill this in. We have a radical, and the other fragment is the cation, because this was a radical cation. Okay? So this process is called fragmentation. Now, I guess I have a spot to define that there as well. So that's when the molecular ion peak breaks or fragments into radical plus cation. So those are we see the molecular ion peak sometimes, but not always. We will see the cation peaks. What peaks? Sometimes they'll be taller than others. What we know about carbocation stability will play a role in understanding which peaks are going to be formed, and we can predict that. There's another term I want to throw out there before, so that we could start getting in there and doing some problems. The base peak is not the same as the parent peak. The parent ion, or the molecular ion, is the ion that came from the original molecule, and it just is now charged, so it's showing up, lost 1 electron. So I'll expand that here, equals OG, the OG molecule that lost an electron before it fragments. The base peak, that is the peak that is the tallest. It does not mean it is parents. Sometimes students want the parent to be the tallest because it's a parent, but no, actually sometimes the parent's so short we can't see it. But sometimes the base peak is the parent. It has nothing, they have no tie to each other. The base peak is the most stable carbocation usually, because it is, what does the base peak mean? It's the tallest peak. The tallest peak means the y-axis is the highest. Since the y-axis equals percent abundance, it means it's the one we get the most of. And so when we find the tallest peak on the spectrum, we call it the base peak. And the base peak, we assign that value 100%. It's relative, right? And I'm just going to say this right here. It's usually not the parent. Doesn't mean it can't be, but most of the time it's not, because it could be so many other things. Okay. So things we get. So I'm going to show you this, and then we'll go back to that list, just so you get an idea. This is a mass spectrum. This is the y-axis. This is the x-axis. Mass to charge ratio, m over z. So charge, for the ones we'll be doing in this class, is going to be +1. But yeah, if it was multiply charged, we'd have to divide by a bigger number. Like you could have something that's +6 charge. You'd have to divide by 6. But for this class, we're just going to do +1. So you don't have to worry about that. So it's basically the mass. Okay. Intensity, percent abundance, basically. And so our peaks that we find here correspond to cations. And then notice the height difference. That simply means this is the most abundant. That must be more than likely the more stable carbocation that could form out of all the fragments that you can make. Now we're blowing this thing apart. We're going to make some horribly unstable carbocations, but it's like that's why it requires so much energy. So don't be put off by that. We have to form the carbocations. They are breaking apart the molecule. However, we can see there's still favoring of the more stable ones. So that's interesting that has that preference. Okay, so I'm going to go back to, before we label that mass spectrum, I want us to keep in mind our two big goals. So the two things, like, we know when we go in and do an IR, we're trying to look at the functional groups. When we're going to get an NMR, we're trying to figure out the skeletal structure. What are we doing with the mass spec? So usually we want to walk away from the mass spec with one of two things, or both would be even better. Okay, so molecular formula. That would be wonderful. So in prior examples up to now, you might have been given the formula, but that's not realistic. Like if you walk into the lab with this mystery molecule isolated from some Amazon, plant or new fungus or something that you wanted to see had interesting properties, it would not have the molecular formula written on it. So you had to find that out. And it's really awesome that you can actually get that information. You can't get that from the other spectroscopic techniques, so you can get the molecular formula. How do we get that? You'll see that. That's the molecular ion peak details. You need the M+, and you need high resolution information, like several decimal places, in other words, to understand what's going on in order to get the molecular formula. You won't necessarily always get that, so that means you should instead look for structural hints. So in other words, look at the fragments that formed. Try to put it back together. Okay, so fragmentation patterns, that's the lower end. So we look at the M+ region and we zoom in and we look at everything that's going on in just that region. That gives us the molecular formula because that's the M+. That's where it's intact. That would have the mass of the whole thing. And then when we're done with that, we zoom back out and we look at the whole thing and we look at all the other peaks, and those give us the fragments, which are the pieces we could put back together. Okay? Let's put that in action. Acetone. Reasonably simple molecule, but it has some interesting behavior in the mass spec that's makes it a good first one to look at. Okay, so let's take a look. So once again, remember the y-axis is the relative intensity. The x-axis, I'm going to write that out. This is mass to charge ratio. Charge, assume Z is going to be +1, unless it's a weird challenge problem that comes up that's, for this class we're going to be focusing on +1. The mass is really what we want to get from it. Okay, what do we know about acetone? Well, we could calculate the theoretical molar mass, right? We do that, then we would know, okay, we should find a peak over around here, because look at how it's intact here. An electron doesn't weigh enough to actually take off anything, so we should calculate about 58. And then there's something else here at 59, so that'll be interesting to see. And then notice there's the tallest peak here. So let's start labeling some of these things. Okay, so first, you'll want to say, what do I expect the molar mass of acetone to be? 2 times carbon plus 6 hydrogens, 6 times H, and 1 times O. So carbon, we're going to use their exact masses of their most abundant isotope. So in other words, we're not using the periodic table. Because this is mass spectrometry, it actually picks up on every isotope and gives them separate peaks. So the most likely peak of the tallest peak in a collection of peaks is from their most abundant isotope. So we know carbon, for example, has carbon 12 and carbon 13. Look at the periodic table, it's 12.01. But then it's averaged of the isotopes. So who's contributed to that value more, carbon 12 or carbon 13? Definitely carbon 12, right? Because otherwise, if you average 12 and 13, if they were equally present, you'd have 12.5 on the periodic table, and we don't. So we are going to use the most abundant one, and I have a list for that for you to use later, but just to get us started. So that would be 24. Same with hydrogen. We know deuterium's out there, but H1 is more prevalent. So 6 times 1, that's why we have 1.008 on the periodic table, right, for the average. So that's 6. Oxygen, we'll use 16, exactly. So no, the math's easy. You don't have all the decimals to add. You don't really need a calculator. But you can use one if you feel like it helps. So that's 40, let's see. I missed my H, 16. 3 carbons, I messed up, 3 carbons. There we go, 36. I knew I was going to be off because I had peaks way heavier than that. So 18, 58. Okay, let's look for 58. Here's 60, 59, 58. Okay, there it is. That's our M+ peak. It's the tallest one in the heaviest region. Heaviest is the farthest along on the x-axis because this is mass increasing, right? So the heaviest it could ever be is with all of the atoms still attached, no fragmentation yet. So why is there something heavier? In fact, it's at 59. But it's hardly, it's such a little abundance, and there's a little tiny one there too. Why? And so we'll see a lot of tiny ones, and we're not going to label all of them, but will focus on the M+ region. Why is there something so small that's actually heavier than this? Well, that comes into these exact isotopes. Those less abundant ones, hence shorter on the y-axis, still do show up. So you're going to see lots of peaks around here, and we're going to actually use that to our advantage to understand what's going on. So the M+1 peak will be very important. So that's the M+1. Who is our base peak? Maybe the only one with the arrow left? Well, not just that reason. The tallest one, right? Now, if we're analyzing all of this, we can see why we have the arrangement that we do with the base peak labeled to be that one. Its mass, 41, 42, 43, matches this well-known cation. This is called the acylium ion, and it doesn't look so lovely at first because we're not used to accepting this as a resonance structure we would really like. But look at how, like I said, we have to fragment it, so it's going to happen. So there's the resonance stabilized cation. So it's resonance stabilized. So of all the cations we form, so notice we form the M+, and it's already kind of started to fragment. This forms the most stable cation of the 2 possibilities left. So we could either form a cation here, but it's more stable to have a cation on the carbon that's the carbonyl than to have a methyl cation, which is like the worst, which is why its percent abundance is much lower. This is a really well-known one. It actually shows up a lot. It's a good hint that a carbonyl is present with a methyl group attached because, you know, some sort of ketone with a methyl, like a methyl ketone, that will be a base peak of 43, acylium. There's a few we'll want to recognize. We'll just see them and they'll be really nice clues for us. So we'll go through that soon. Acylium's one of them. Okay, so we're going to break this into pieces. We're not done looking at them, don't worry. M+, when we look at the M+ peak, once again, it gives us our molar mass because that's the heaviest thing. That's this one. All right. I have the hand. Let's see. There we go. Gives us our molar mass. So 58 matched. And we won't know that it's acetone always in the future. We're just comparing what something we know looks like in the future. We'll try some unknowns. 58. So M plus gives us our molar mass. There's something really useful you can get from the molar mass. Let's suppose we didn't know the structure. We didn't know it was acetone. We could at least find out something about whether nitrogens are present or not, and that's because of the nitrogen rule. So turns out that if you have an odd molecular weight, you have a different number of nitrogens, you can conclude something about the number of nitrogens, I should say, than if you have an even molecular weight. So what rule am I going to do? I'm actually going to slightly derive it for you. Just kind of demonstrate it anyway. It's because nitrogen has a different valency. It makes 3 bonds. So it has that effect on the overall mass when it's making 3 bonds once or twice. So it's either making, if you have 2 of them, you're making 6 bonds. If you have only 1 of them, you're making 3 bonds. So you're making either an odd number of bonds or an even number of bonds, depending on if you have odd or even number of nitrogens. So for example, look at something like this, propane, 0 nitrogens. Its molar mass is 44. Okay, now let's take propane and replace 1 carbon with a nitrogen. What did that do to its mass? Everything else was the same. We just altered the hydrogens as needed. What did that do to its mass? Odd. Very close, because carbon and nitrogen are close, 14 versus 12. So yeah, you say, okay, well, wait a minute. Nitrogen has an even mass, but it makes an odd number of bonds. So that's where that comes out. It manifests itself with the odd number of bonds. 2 nitrogens. We go back to even. So it's just that math rule we know about, that if you multiply something or have some odd amount of substance present or numbers present, then you get an odd answer. But when you have 2 odds, you end up with an even. So same rule. It's as simple as that, really. So the odd molecular weight is the only informative thing. It means we have odd number of nitrogens. Even molecular weight means we have 0 or even. I mean, that's still informative. We just don't know. We just don't know if we have, like, for example, acetone, 58. Okay, so we either have even nitrogens or no nitrogens. So we have no nitrogens, so that worked. We know we didn't have an odd nitrogen. So information is good in any form that it takes. But yeah, the odd is particularly informative. So when you see an odd M+, you must have nitrogen. You must have an odd number. So that's very useful. Okay, so where did I get those numbers from? Remember, I talked about our mass numbers we're going to be using, because you're going to be doing some simple math, adding up to find out the molar mass. You're going to use the most common, so here's the table we'll be referencing frequently a lot. It'll be our reference table. So you might, it's on the spectroscopic data sheet. You might want to bookmark that again and take a close look at it, copy it, have it somewhere else as well. We'll be using this a lot. So how do we interpret this table? I'm going to change this to arrow or red just because it's there. So these are the atoms we'll be looking at. So we're not going all over the periodic table. Of course, hydrogen, carbon, nitrogen, oxygen. Those are kind of our go-tos. We will do the halogens. Maybe occasionally fluorine and sulfur to a lesser extent. Okay, so don't worry about anything else other than these. Now, look at their natural abundance. So these are the dominant ones. So 1H, far more abundant than 2H. Look how that comparison, that ratio. It's almost insignificant, right? But it's not when you can pick up on it, when you have a sensitive instrument. Carbon 12. Okay, well, you know what? There's a little more carbon 13 than 12. 1.1, that's much more significant. Nitrogen, more than hydrogen, but much less than carbon 13. So what am I looking at? I'm looking at the next isotope in its abundance. So there's 3 forms of hydrogen, and carbon 1's the only one, hydrogen 1's really the most significantly present one. So in other words, when you're calculating your masses and you want to know what the M+ peak should be, you're not going to go to the periodic table. You're going to go to this chart or remember what the most abundant one is. And this is the value you use for M+. Those are the most abundant ones. If you want to say, okay, I need to know what that heavier one was, the M+1, we alluded to that, we found that. you have to use one of these. Notice how that would be enough to increase your mass by 1. So in other words, you'd say, okay, I have propane or even acetone, and then one of the carbon atoms was 12 was replaced with 13. There you go, you're +1, so M +1. Doesn't mean all of them are made with that, because that's statistically very unlikely, and if it did happen, it would be such a small peak in percent abundance that we don't pick it up. But to have a significant peak that we actually see, that's the next most abundant thing possible, means that one of the most abundant ones was replaced with a less abundant one. Which one? Most likely the one that's most abundant here. Who's most abundant here? Well, let's see. Just look for the biggest number. Carbon, right? So carbon clearly is the winner, the most abundant M +1. That answers that question right there. Okay, so that's going to be important in our analysis. And finally, there are some, but you notice some of these got knocked out of the running. Like there's no M +1 for fluorine, chlorine, bromine, iodine, but the halogens do have M +2s. And notice how abundant they are. I mean, we're not talking about 1%. In fact, it's nearly 1-to-1 with bromine. And that's still pretty significant. Chlorine is a 3-to-1. So we will also use that to our advantage, that unusually high relative abundance of the two different isotopes, to help us decide if bromine or chlorine are present. The rest of these are so insignificant that it's hard to pick up on them, except for maybe sulfur, because that's a 4%. That's pretty big. Let's see, let's circle that one now. M +2, so that's 2 higher than its most abundant isotope. Okay, let's start using that. Like I said, we're going to use that information to help us. How does M +1 help us? We'll start with that one. We already talked about how M+ helps us. M+ helps us get the molecular formula, molar mass of all of the most abundant isotopes, but the lightest ones being these in this column right here. When would we ever integrate these into play? Well, notice out of all of them, carbon's the most abundant, so that's the most likely substitute for one that is giving rise to an M +1 peak. So in other words, if we see an M +1 peak because we have a high enough resolution region of that spectrum, we should be able to find out information about carbon. Actually, very important information about carbon. The number of carbons. That's huge. That's part of the formula right there. Sometimes takes a little more playing with the math, but like I said, it's not complicated math. It just takes a little time. But look at that again. If we have an M +1 peak, who's responsible for that M +1 peak? By and large, mostly carbon. So we're going to take advantage of that and ignore the other ones. Yes, they contribute a little bit, but not as much as carbon. And we're going to say, okay, so whatever that peak is, whatever percentage is, if we divide it by 1.1, we could find out how many carbons are there. So that's where that comes from. So for example, let's do this one. Propose a formula that for compound that has the following peaks in the mass spectrum. Okay, so let's not jump to the formula yet. Let's just even say predict number of carbons. So let's say it's CX, and we don't know what the H is. HY. We could at least get X. Let's start there. We'll get to the whole formula soon enough, don't worry. If you want to know the number of carbons, you have to have the M +1 information. If you don't, you can't get the number of carbons that easily. You have to get it a different way. Like maybe it's given to you, but yeah. Since we're in this section, it's probably not. So you take the M +1% from the mass spectrum, and you divide it by 1.1 because that's from the table that that number right here, that highlighted number, 1.1. You don't have to have that all the way 1.107. Okay, plug it in. M +1. M +1 peak was at M over Z. So M over Z was at 68. Notice that's already at 100%. M over Z is 69. M plus 1, notice this is 68. M plus 1 is 1 higher, 69. Notice that the percent is 4.3%. So take that number and you put it in there. You need to calculate. So 4.3 divided by 1.1. And yeah, you might want to pull out a calculator because you get more into decimals here. So it's about 3.9 numbers of carbon. So since we can't have that many, we would be safe to say it's probably 4 carbons. What if you get 3.5? What should you do? You should test your formula for 3 carbons or 4 carbons. But hey, that's still a gift. You get to know something closer about, it could have been 10 carbons. Now you know it's 3 or 4, right? But this one, 3.9, is close enough that it's more than likely 4. I would stick with 4 unless you were forced to reevaluate that. So usually that is a good rule of thumb. Okay, so 4 carbons. So that gets you on a good start for the formula, right? Okay, before we do the whole formulas, I want to go back to this chart. Okay, now we know why we use M plus 1. We almost exclusively just use that to find number of carbons. We use M plus to find molar mass or molecular weight. Why do we use M plus 2? I'm going to highlight the standouts in M plus 2. M plus 2 standouts, by and large, these guys. Sulfur, fine. But really look at that chlorine and bromine. I mean, that's a huge percent contribution. We're not going to look at M plus 2 and even care at all about how that tells us about tritium, H3, or carbon 14. I mean, that's such a tiny percentage, okay? Oxygen, you can sometimes use it as well because 0.2 is pretty good, but it's only useful if these aren't present to swamp it out. So how are we going to do that? So remember that we have bromine, chlorine, bromine 1:1, chlorine 3:1, sulfur is the 4% one, okay? So let's try it. This is the M plus 2. Now let's get another mass spec here. When is M plus 2 useful? So we're giving you the structure, and we're not even looking at fragments yet. We're looking at this region. We're talking about M plus 1, M plus 2, and any other M pluses we find, the molecular ion region. So when we're looking at just the molecular ion region, we're really not looking at fragments yet. We're trying to get a molecular formula. It's already here, so for right now, because we're learning the first stage of it, we're trying to associate it. But without this information, we can actually get this information back. So let's try to see how this was labeled, because you want to be able to do that in the future. So this is the answer. This is what bromopropane looks like. How would you know how to assign each of those? So let's zoom in here. You got to look at your M plus region. Now notice there's even right there little peaks, and that's not to be ignored. That's actually an M plus 1. Hello, carbon 13, right? And this is an M plus. This is M plus 2. This is 1 after M plus 2. That's M plus 3. That's the carbon 13 version of the M plus 2 peak. Okay, let's spell that out. What we're going to do is write out bromopropane in every bond without bond line format, which might feel like torture if we've been writing it so much faster, but we have to because we have to see the isotopes. So we're going to write it out 4 times because there's 4 peaks. So I'm going to call this A, B. Oh, my poor cat is meowing. He wants to come in our lecture. I wonder if you guys can hear him. I should let him in. Well, I am going to write these all out. And if he's still meowing, oh, he's poor thing, he's meowing. Okay, so this will keep you busy while I let my cat in. I don't mind, if you don't mind, if He joins the lecture. All right, so copy those down, and then I'll be back. What? Coming? All right, here he is. Are you happy? Now, because the door's closed, he's going to want right back out, I bet. So there we go. All right, let's label these A through D. We have 4 peaks. We wrote these same 4 molecules. What's the difference? Notice a little bit is kind of hinted at here. The reason we have a separation of 2 in the mass, 122, if you add up the masses, remember we're using the lowest, most abundant isotope to get the first peak, the M+ peak. 2 higher than that would be caused by the presence of the other isotope of bromine, which is 2 higher, right? So the 81 bromine versus 79. And if you look at the periodic table, they're averaged to almost 80 because they're present in 50-50. We'll address that too. So we know what M+ should be. Let's label that out. That means we're going to label all the carbons and the bromine isotopes. We're going to have carbon 12, carbon 12, carbon 12, everything the lowest possible. That's easy, 79. That adds up to 122. All right, so now we're going to say, what is M+? So this is M+. M + 1, how do we get that? We don't have 81 bromine, we must have 79 because that would make it M + 2. The only thing that's M + 1, remember what M + 1 is for? For carbon, carbon 13. That means one of these 3 carbons. Pick a carbon, any carbon. It doesn't matter which one. It happened to be carbon 13. So they would all give that peak, whether it's this carbon, this carbon, this carbon. So there's some percentage of them, precisely 1.1%, that have a carbon 13 replacing a carbon 12. So let's label that. I'm going to actually pick the middle one, 12, and then I'll make it red just to stand out. So the M + 1 is thanks to our carbon 13 presence. What is M + 2? M + 2 is the difference of 2. Bromine differs by 2 with its isotope. That means we can't have any carbon 13 there, because then that would be a difference of 3. We'd have a difference of 1 from the carbon 13, and we'd have a difference of 2 from the bromine. So we have to go back to all carbon 12, 12, 12, 12, 81 now. That's M + 2. So remember to compare it back to M+. The difference between these is 2. So let's put that mass also, 123, 124. So this is a difference of 2, which means it can only have 2 AMU difference, which bromine provides. Someone might say, what about 2 carbon 13s? Sure, you could do that, but it's very unlikely because the abundance of carbon 13 is already so low, it's even less likely that 2 of them will be carbon 13. So that would be an incorrect assignment, especially because look at the percent abundance. Indicates a 1-to-1 ratio. That means these are almost, it's a little off from 1 to 1, but very close. So this is not from carbon 13. The reason this is so short is because that's from carbon 13, the little ones. The tall ones are from a very abundant isotope. So hence the 81. I was going to do that in red to help it stand out too. There we go. All right, last one, M + 3. What does the M + 3 look like here? Let's label it. We know it tells us it's 81 bromine. It's the heaviest thing there. So that means that we got 1 of each. So we were 3 off. We've already kind of alluded to that, right? 3 off from here. It weighs 125. So we have +3 to deal with. 2 can go to the bromine isotope, and then 1 can go to the carbon isotope. You say, wait a minute, bromine has a high abundance. No, but look at these guys. These are another pair. They're 1-to-1 to each other. These are 1-to-1 to each other. So you have 2 pairs of 1-to-1 ratio. These are so little because they have the carbon 13 in it, and that's less likely to form. These are so high because they have only carbon-12, and then they have the two equally abundant, almost equally abundant bromine isotopes. Okay, let's fill that in and reflect that. 12, and I'll make it different this time. 12, I'll make that one 13, and then this one 81. So those red numbers take us off the original M+. Okay. All right, so what can we learn from this? Bromine's one rule you want to spot right away. If you see that M+ region, and it's not just one peak, it has a twin almost. Those twin peaks, that is a sign bromine's present. Okay, that's like a special delivery package handed to you to give you a lot of information that knocks out a lot of molar mass too. So 1 to 1. 1 to 1 in the M+ was 1 to the 1 M + 2. We also saw, so that was these two, M+ and M + 2. We also saw 1 to 1 with the M + 1 and the M + 2 of the M + 1, namely M + 3. Why? Because this was 81, 79, excuse me, 81, let's put it in order, 13, 81, and this one was 13, 79. This one was 12, 81, and this was 12, 79. So all the isotope combinations possible. The most abundant are the tallest, and that's why we have the y-axis to tell us that. That helps us distinguish between them. Okay, so we saw chlorine actually had a very similar diagnostic isotope distribution. Very useful. So I would like you to repeat drawing it 4 times on your own. Try that out. Do the same thing I did above. Okay, you could check that. But notice the only difference between what's going on with chlorine and bromine, I mean they both differ by M + 2, is the ratio. So notice that what's going on here is we have an M + 1, so it's 80, where's 80? Yeah, M + 1, and an M + 2, and it's kind of hard to see anything past that with the M + 3. And sometimes we have little other ones that we don't need to worry about, but yeah, it's so short we don't even see the other one. So the M+, and because it's this one would be a third of that tiny thing, so it's not visible. So you could draw out 4 if you want, but we only need to draw out 3. Yeah, I'm going to do it with you. I actually think that part might make it harder in retrospect. It's different when it's in a video. Okay, so what's going on here? Look at that peak height. That's the 3 to 1 ratio. In our table, we saw 75, 25, 3 to 1. 3 to 1 what? Chlorine, 35, that's the more abundant one, versus the less abundant chlorine, 37. So if you made that 100%, it'd be 75% of the chlorine you found in any sample would be chlorine 35. The other 25% would be chlorine 37. That's reflected in this peak height that we see here between these two. They differ by a mass of 2, right? All right, so what I'm going to do is go ahead and draw out and label these. M+ is 78. M + 1 is not labeled, equals 79. M + 2 is 80. And M + 3 would be 81. Why don't we see M + 3 this time? Okay, so this is our M + 1. And if the M + 2 to the M + 1, in other words, its M + 2 has to be a third, it's a tiny little speck compared to, so we actually just, it doesn't have the resolution to see it. We see that, try to get a third of that, you're not going to see it. So it theoretically exists, but so you could draw out what it would be if we picked up on it, but it's not there. Too low of an abundance. It has every instrument has its limits, so that's why you hear about this high resolution or what resolution, that sort of thing. So okay, so this has been drawn out for you. You can draw it in this formula if you like. You could actually draw the 35 on the chlorine. This has been drawn out for you. But what does this mean? This means all the carbons are 12 because those are the most abundant peaks possible. 12, 12. How do we get the 79? I'll draw that one out for you. What would an N+1 look like? So we draw the chlorine, the C, the H, the CH3, the H3C. So if this is our N+1, that means we have exactly what our N+ is, and only one off. It has to be the carbon that's different, carbon 13. It's always the carbon. That's our N+1 isotope, right? So everything else is 12, or its other dominant isotope that's lower. Okay. All right, bromine, chlorine, famous N+2 region. That's where, why do we look at N+2? Bromine and chlorine is the main reason. Okay, finally we're going to get to fragmentation. So fragmentation is great because we get to figure out the pieces. So we're zoomed in on the N+ region, and now we're going to zoom out and look at the whole thing and all those other little peaks we weren't looking at earlier. All right, so taking another visit at fragmentation, we had kind of a generic template before where we had the R's drawn in. Now here's a real one, and we'll draw the little mechanism of it. Okay, let's draw this breaking apart into component pieces. So let's fragment right here. Why did I pick that spot? I need to make a carbocation. I need to pick one. I like the looks of that T-butyl. That's much better than anywhere else I can think of. But, you know, realistically, we didn't get the greatest radical either, primary radical, but that's what happens when you have a high energy destructive force coming into your molecule. Okay, so a lot of times we have to see how that rule of thumb, we have to reason through it. Cleavage, which is breaking the bond, favored alkyl substituents to give that stable carbocation. So I looked for alkyl substituents. I broke it there to try to get a nice carbocation. So we see that peak there. There are some that are so commonly formed because they're such stable, relatively stable carbocations, or even just cations, that they're worth recognizing. So in other words, so you don't have to get your calculator and add it up and say, oh, what has a mass of 77? Well, it's worth just kind of doing enough problems or having a little list of all the fragmentation patterns. I lost that. To say, hey, I could do that. That's got to have a benzene. Thank you for the clue, right? So if you see 77, that's usually benzene. It's not guaranteed. Other masses can add up to 77, but if you see a base peak of 77, really abundant, then that's a sign you have it. Or you might see it as one of many peaks. Here's an example. So we're looking at fragments now. Notice I am too zoomed out to look here. I don't know this information very well. I don't know what those numbers are. And so this is an example of a mass spec where I'd be looking at the fragments, not just the N+. The N+, I could say, oh, it's about 120-ish, but I already have the structure. I'm going to try to assign what these fragments are. So I have a 92, I have a base peak of 91, and I have a 77. So that's my benzene. And the 91 and 92, what are those? Let's get to the bottom of those too, okay? I didn't give this one to use an example, so I'm not going to spend a lot of time writing on it. I just want you to see what it looks like in real life. So this is an odd one. 91 is tropylium, which we studied in the aromatic section for a reason, because it's a commonly found rearrangement that happens when we make a benzylic carbocation. So it can actually, you know, open up like that. So it's not primary anymore. And then you have this still aromatic 7-membered ring with more delocalized electrons, and the positive charge is not concentrated on a primary carbon. And so that's a 91. Very common base peak. If you see tropylium, that is not what's in your structure. That's what it rearranged from your structure. Your structure has at least a toluene unit, or a benzene with a carbon. Okay? So if in original structure, if you see this in the mass spec. So in other words, We see that 91 right there. That's the tropylium ion. What's 92? That's a less common one, and notice how it's lower. So if you have more than just one carbon attached, which you know it's reasonable to expect, we won't always just have toluene. I'm going to skip to the fragmentation radical cation. So let's say we have something kind of like this. So that's how we have that kind of sorted out. I'm going to redo this one right here. My pen stopped working. Okay, let's fix this. Okay, so here we go. Radical or cation. Okay, so let's skip to the okay, so we could have a radical cation form as a result of a benzene, and then there's an additional, if there's extra carbons on there, then this hydrogen, this rearrangement can effectively happen. So, and it can help release like ethylene or small molecule gas. Plus, because notice it picked up that hydrogen more than it had, that's the +1. That's where that comes from. So if you see a 92. So that means a benzene plus alkyl chain substituent. So notice that's why I brought up this example, because a lot of times students want one or the other. Well, which one will I see? Well, look at how this, we saw both. 91 is the way more obvious one, but that 92 always kind of accompanies it often, and it's kind of mysterious. So that's why I bring that in. And then 77 we know is benzene. So we have already assigned most of those fragments. We're not going to make it the business to necessarily assign all of them, but the ones that are reasonable to predict, we will. Acylium. Okay, we will see acylium. That means we could have had, you know, it doesn't have to be protonated. I don't know why I have that only. Anything with a methyl ketone, you know, as part of the structure, you will see acylium. So that's the 43 mass. Just don't be lured into comfort with 43. If it's a base peak, it's very likely acylium. But use your other spectroscopic techniques. Make sure you really have a carbonyl. Make sure you have an oxygen, right? But because other things have a mass of 43, and some that are very common, like propyl groups, right? So the mass matching is not a guarantee. You have to kind of compile all your evidence to make a reasonable guess, right? And then once it's overwhelming that they're all supporting each other, then you've got your structure. Okay, so I am going to stop here. I would like to, no, wait, I'm going to go back to the beginning. All right, so hopefully we've had enough information to start doing some problems. What are ways that we can tell the difference between, this is the question I want to leave you with. Think about everything we've talked about. These two compounds have the same mass. They're not isomers. They're not related any other way. This has 50 AMU, and this has 50 AMU. So it's not all about the M+ peak, in other words. That means they have the same M+ peak. So that will tell us nothing. The M+ alone will tell us nothing on the mass spec. But the mass spec will give us more information than just the molar mass. It will help us understand the difference between those two. How would the mass spec of those two be different? I'll leave you with that thought. Think about it. Make a list. 3 ways, 3 different reasons, okay? How does the mass spec of those 2 compounds that have the same mass, how does the mass spec differ? Okay, I'll leave you with that thought and see you soon.
Poiché